Okay, everybody, I'd like to talk a little bit about how we use the log function in econometrics. And first, we'll do sort of a little bit of the theory, and then we'll pop over to R and see how we might actually do estimations using R. So there's three specifications that will use the log function. Remember, a log function transforms a variable into the log of that variable. So it's a transformation of a variable. So we could either transform the x variable or the y variable or both of the variables. So we could take the x variable and calculate its log and use the log of the x variable as the explanatory variable, or we could take the y variable, transform it by using the calculating the log of the y variable and using that in regression analysis, or we could have the log of x and the log of y as our two explanatory variables. Each one of those cases, three cases, will generate different interpretations of the coefficients that we estimate. And let's take them in turn. It's pretty straightforward. It's kind of a rule that you have to memorize. It's not really all that intuitive. So I encourage you to practice and memorize these three cases and how the interpretation goes in the three cases. So we'll start with the log linear specification. So in the log linear specification, we have the log of y. I can make this a little bigger. Um, and yeah, that's better. And I can get my annotator here. So we can have the log of y as the outcome. So we take the log of y, and that's the outcome. And as before, we have the regular x variable as our explanatory variable. So we're going to estimate then a coefficient beta 1, right? We'd have beta 1 hat if we had data and we estimated it. And we're going to interpret beta 1 as the change in the log of y. So it's the change in the log of y for a change in x. Now remember, the change in the log of y, we said in the earlier video, can be interpreted as the proportional change. Alternatively, we can multiply both sides by 100. So we have beta 1 times 100. Let me switch to the non-disappearing one. So we have beta 1 times 100 on this side, and that's going to be equal to the proportional change times 100. But what's a proportional change times 100? That's just the percent. It's hard to draw here on my graph, so I'll use percent delta is the proportional change times 100. So the denominator is unchanged. So we can think of, if we multiply the estimated coefficient by 100, that's the percent change in y for a 1 unit change in x. Or if we don't multiply by 100, it's the proportional change in y for a 1 unit change in x. So pretty straightforward interpretation of that. And let's go on to our next interpretation, which is the log specification. So both the outcome and the explanatory variable are in logs. So how do we interpret the coefficient beta 1 that we estimate when we do that? So beta 1 is going to be equal to the change in the log of y over the change in the log of x. Each one of them is a proportional change. We can write the change in the log is the proportional change in y. So we interpret the coefficient beta 1 as the proportional change in y for a proportional change in x. And that's the same thing as a percent change in y over the percent change in x, because we can multiply top and bottom by 100. The equality stays the same. So beta 1 in this specification is the percent change in y over the percent change in x. There. So in economics, we interpret that as the elasticity. So a log-log specification means we interpret the coefficient as the elasticity. What's the percent change in y for a 1% change in x? And finally, we have our third case. Let me erase everything here and scroll a little bit down. So our third case is the linear log specification. So our linear log specification, we have sorry, it's on the erase here. I need to get, yeah. we have the y variable is unchanged, but the explanatory variable, the x variable is the log. And now we're going to interpret beta 1 as the change in y for a proportional change in x, a proportional change of 0.01. We'll usually multiply this by 100, so it'll be the change in y over the percent change in x. But to do that, if we're multiplying the denominator by 100 here, it means we have to divide this by 100 over here for them to be equal. So we'll say that beta 1 divided by 100 is the change in y for a 1% change in x. So it's the change in y for a 1% change in x if we divide this by 100. And that's the usual interpretation we might have of the linear log specification. You should read these in the textbook. As I said, there's not very much intuition about these. You just have to memorize them, but there's only three cases, so it's just three things to memorize. The log linear case, the log log case is the elasticity. Probably you've already memorized that. And just by repeating it, right? Log log elasticity, log linear. We can sometimes think of it as the growth rate. And then we have the linear log, which doesn't have an obvious interpretation in economics, not an obvious example. The Mincer equation is the log linear specification of the earnings equation. So it's sometimes called the Mincer equation. And that's real useful. We have the outcome variable measured in logs and the explanatory variable years of education measured regular. And remember what we just said. So that's a log linear specification. So if we multiply the coefficient by 100, so say the coefficient's 0.03, we multiply by 100, that means for each additional year of education, there's a 3% increase in earnings. That's our interpretation. So for each additional year of education, there's a 3% change in earnings if our coefficient were 0.03. We multiply the coefficient by 100 and interpret it as the percent change in the outcome for a 1 unit change in the explanatory variable. When we have dummy variables, things get more complicated. And I'll leave those for another video, perhaps. You might look in the text to see about the interpretation of dummy variables when we have log specifications. Obviously, we can't take the log of a dummy variable because the log of 0 is not defined. So always remember that. If we have dummy variables, it's going to be the explanatory variable that's the dummy variable and the outcome variable that's the log. We can't take the log of a dummy variable because a dummy variable takes on value 0 and the log of 0 is not defined. So there's only one case to consider when we have dummy variables.